Hi, my name is Dr. Tishan. In this video, we're going to do two examples of writing equations of tangent line to a curve at a given point. Let's go ahead and take a look at our first example. We're going to work with the function x squared plus 3. Now, what does that look like? All right, when you graph the function y equals x squared plus 3, or f of x equals x squared plus 3, it's a parabola shifted up 3 units on the y-axis. So here's our parabola, and our given point here, 1, 4, we want to write the equation of the tangent line passes through this point. So on our parabola, I went ahead and plotted the point 1, 4, and I drew the tangent line. Tangent line is a line that intersects the curve in exactly one point. So here's the tangent line in green, and we want to write the equation of this tangent line. So to write the equation of a tangent line, we need to know a point on the line, which we do, 1, 4 is given to us, and we need the slope. We need the slope, okay? And we'll use the point slope form because it lends itself so well to this style of problem. How do we find the slope? Well, the slope is the derivative of the function. So you have shortcut methods that you learn in calculus class with the power rule, product rule, quotient rule, and so on. But we're going to do this the long way, okay? So we're going to use the definition of derivative to figure out what the slope is. And we're going to use two different methods, okay? This is going to give us the derivative of the function in method 1, and then we're going to actually evaluate it at the point. Method 2 actually it gives you the derivative directly at the point. So we're going to have two ways to get our slope that we need. We've got our point, but we need our slope. So let's take a look at the first method. So to get the derivative of the function first, we're going to take the limit as delta x goes to 0. F of x plus delta x. So we're going to take our function and substitute in x plus delta x for the x here. So you're going to have quantity x plus the delta x, and we're going to take that quantity, square it, add 3, okay? We're going to subtract from that the function, and the function is x squared plus 3, okay? And then all this goes over delta x, all right? When evaluating limits, you would take the 0 and substitute it directly in for delta x, and you would get a 0 over 0 indeterminate form. So we would need to simplify our function here, the difference quotient. And when you simplify it, the best way here to simplify is to expand, to multiply out. So let's do that in the next step. So we're simplifying. So our derivative is going to be the limit as delta x goes to 0. All right, when you expand this, you get x squared plus 2x delta x plus your delta x is squared plus your 3, and then distribute the negative sign, so minus x squared and a minus 3. So we had to take the numerator and completely expand it. Your denominator has the delta x in it, okay? Then let's take a look at the numerator here. Let's see what can we do here. Can you see the x squared? This is a positive x squared, and here is a negative x squared. They cancel, okay? This is a positive 3 here and negative 3 here, and they cancel, all right? So, and what do we have left over in the numerator once we cancel those common terms? We have a 2x delta x and a delta x. We can factor out the delta x. So you have the derivative of your function. It's the limit as delta x goes to 0. When you factor out the delta x in the numerator, you end up with factor out the delta x, you have a 2x by itself here, okay, and then a delta x there, okay, and all this is over delta x, all right? Your delta x is canceled, all right? So then when you go ahead and substitute 0 in for delta x, your derivative of the function is just 2x, all right? So if your function is given as x squared plus 3, then the derivative of this function is 2x. That's the derivative of the function. Now we want this derivative. We want to evaluate the derivative of this function when x is 1, okay? So to get the derivative at the point, you're going to plug in the x coordinate. So we want to evaluate this derivative. It gives us the slope that we're looking for. We're going to use a definition to get the equation for the derivative, plug in the x coordinate. So the x coordinate for this problem is 1. We plug it into our derivative. So our derivative says take the x and double it, multiply it by 2. So here is the slope of the tangent line that we need. The slope of our tangent line. So the point we're going to use is 1, 4. The slope that we need is 2. We found this slope by finding the derivative of the function and then evaluating the derivative of the function at the given point. There is another way, maybe a little bit shorter, a little bit of a shortcut. Instead of finding the derivative of the function, evaluating it at the given point, you can use this formula here. This is another method. This gives you the derivative right right at the point. So the C value here is the x coordinate we want the derivative of, right? So just to demonstrate, we're going to find the derivative. We know the slope is 2, okay? Here's another way to get it. So we want f prime. We're going to plug in at 1 because we want to evaluate at the x coordinate of the function. So this is going to equal the limit as x approaches 1, okay? And then you're going to take the function in the numerator, which is x squared plus 3, okay? And you're going to subtract from that f of 1, okay? So you're going to f of 1, which is 1 squared plus 3, because you're plugging 1 into the function. And all this goes over x minus 1 in the denominator, okay? So we want to evaluate the derivative at 1. You're going to take the limit as x approaches 1. Simplify in the numerator, you have x squared plus 3, and then 1 plus 3 is 4, so you're subtracting 4 from here, and you have x minus 1 in the denominator, okay? All right, so we have f prime at 1. It's the limit as x approaches 1 of x squared minus 1 in the numerator and x minus 1 in the denominator. Evaluate a limit, you take the 1, you plug it in, and you have indeterminate form 0 over 0. So we're going to take this function and change its form. All right, so f prime at 1, when we change its form, we're taking the limit, x approaches 1. We can factor this numerator, factor the numerator, it's the difference of two perfect squares, so it factors into x minus 1 times x plus 1, okay? And then the x minus 1's factors cancel, so when you take the 1 and plug it into the remaining factor, you can see that you get 2, which is the derivative at your point. Don't know if it's a shortcut or not, but so you can use the definition of derivative, get the derivative of the function, evaluate when x is 1, or you can go to the definition of derivative at a point. Either way, the slope that we're looking for is 2. All right, so now let's finish the problem. Okay, so finish the problem. What is it that we're looking to do over here? We want the equation of the tangent line. To write the equation of a tangent line, we need the point. We know what the point is. It's 1, 4. It's given to us, and we need to know what the slope at this point. What is the slope of the tangent line at this point? Well, the slope is the derivative of the function, and it came out to be 2. Okay, so what's our equation of the tangent line? It's going to be y minus the y coordinate, which is 4, okay, equals, then you put your slope in here, times the quantity x minus your x coordinate, which is 1. And here it is. Here is your equation of the tangent line. Here is the equation of the tangent line, okay? When you're asked to use the definition of derivative, one of these forms to compute it. All right, and you'll learn power rule, product rule, chain rule. There's other shortcuts, but for right now, this is how you would actually compute it using the longer method. Okay, let's do another example. I have another example on the back board, and if you'd please excuse, I know there's background noise. I'm doing this in my backyard, and there's airplanes. So you can hear the airplanes flying overhead. So I have one more example for us to take a look at. It's on the back board here. All right. And so let's go ahead and find the equation of the tangent line here, all right? So remember from the other side of the board, equation of your tangent line is y minus the y coordinate equals your slope quantity x minus your x coordinate. To write the equation of your tangent line, we need to know a point and we need the slope. They give us the point, we just need to generate the slope, okay? Now, do you want a picture of this? Let's go ahead and take a look at what this looks like. I had a picture on the other side. Let's go ahead and sketch the graph, just really quick sketch of a graph. The function is x minus 1, radical quantity x minus 1. So that means you're going to, let's see, shift this to the right, okay? So we're going to shift this to the right 1 unit. Okay, and so this is what our function looks like. That's our radical graph shifted to the right 1 unit. When you subtract inside the function, you shift it to the right. We want to go to the point 5. We want to go over 5 and up 2. Okay, so 5, 2. So here's the point 5, 2. That's our point. Draw the tangent line to this curve. Okay, so here's the tangent line to this curve. All right, we want the equation of this tangent line. We're looking to write the equation of the tangent line at the given point. All right, so what do we need to do? We need to know what the point is, and we need the slope. Slope is the derivative Slope is the derivative, okay? So let's just do that. We'll get the slope using the definition of derivative, okay? So the definition of our derivative, do you remember what that was? That's the limit. We'll take delta x to 0. It's f of x plus delta x minus the function, okay? I'm making my f's cursive here, all right, all over f of x, okay? So those are just cursive f's. I do that sometimes, all right? So we're going to use the definition of derivative. All right, so our derivative of this function, okay, well, it's going to be the limit is delta x goes to 0. We're going to take the function and make our substitution, put x plus delta x in for x. This is going to be radical x plus delta x minus 1, okay? Subtract from that the function, which is radical x minus 1, and all this goes over delta x, okay? So again, this is your definition of derivative right here, definition of derivative, and we are going to compute the derivative using the definition. We're going to get the slope that we need using the definition, okay? So for you want to take f of x plus delta x, take your function, replace the x's with x plus delta x minus the function over delta x. Now, when you take the 0, plug it in for delta x, when you evaluate this limit, you get indeterminate form again. Indeterminate form, so we need to do here is we're going to have to use something to change the form of our expression here. And what we're going to do is we're going to multiply by the conjugate. We're going to multiply by the conjugate of the numerator. The conjugate of the numerator is going to be radical x plus delta x minus 1 plus radical x minus 1. Keep everything balanced. What you multiply the numerator by, same thing with the denominator. All right, so we're going to multiply numerator and denominator by the conjugate, okay? So you end up with a derivative of the function, okay? When you multiply the numerators together, there's the difference of two squares. You're going to have x plus delta x. We forgot my limit expression. So you have the limit is delta x goes to 0. X plus delta x minus 1, okay? And then minus the quantity x minus 1. This is your numerator. Your denominator, you have delta x. And you have the quantity radical x plus delta x minus 1 plus radical x minus 1. So we're here, okay? Distribute that negative sign in the numerator. See what we want to do next. And we want to just expand the numerator to see how we can combine terms here. So our derivative of the function, okay, it's the limit. I didn't take the limit yet, so I need to keep writing this down. It's the limit as delta x goes to 0. Numerator have x plus delta x minus 1 minus x and plus 1. Here's my numerator. Denominator, you have delta x times that conjugate. That conjugate is x plus delta x minus 1 plus radical x minus 1. So we're here, okay? Combine like terms in the numerator. Combine like terms in the numerator. So you have a positive x, negative x, you have a negative 1, positive 1, these terms all cancel, okay? So these terms cancel, and notice, if I can do this right here in the same step, our delta x's cancel as well. Our delta x's cancel as well, all right? So what do we have for the derivative? We have f prime of x, okay? So it's the limit is delta x goes to 0 because I have not taken the limit yet, and it's 1 in the numerator. In the denominator, we have radical x plus delta x minus 1 plus radical x minus 1. All right, let's go ahead and take the limit. Take the limit. So we're going to substitute the 0 in for the delta x to see what we end up with. Okay, and then so just let me move over to here. Okay, so I'm going to move over here. So what do we have for the derivative of our function? So the derivative of our function, we plugged it in. I don't have to write the limit expression down because we substituted in. So we end up with 1 in the numerator. And if you can see, we have radical x minus 1 plus radical x minus 1. So what does that mean? It means we have 2 radical x minus 1s. Okay, so that's what we have here. All right, so there's the derivative of the function. This is the derivative of our function. Okay, we want to find the derivative at our point. In our point, the x coordinate is 5, y coordinate is 2. To get the derivative at the point, we're going to plug in the x coordinates. So we want the slope of the tangent line. The derivative of the function is the slope. We want the slope when x, we want to replace the x with 5. Okay, so we want the slope at 5. So make your substitutions. You have 1 over 2 times radical 5 minus 1. And so 5 minus 1 is 4. The square root of 4 is 2. So the derivative at 5, the slope of the tangent line at 5, when you simplify it, is 1/4. All right, and that is the slope that we need to write the equation of our tangent line. The slope is 1/4. All right, so let's go ahead and write the equation of our tangent line, okay? We want to write the equation of the tangent line here. To write the equation of a tangent line, we need our point, which is at 5, 2, okay? And we need our slope, and our slope, we computed our slope to be 1/4, all right? So what is the equation of this tangent line going to be? And I think the birds chirping here, waiting to hear what the equation is going to be as well. Pardon the background noise, since we have motorcycles and airplanes and birds and everything. But okay, so here we go. So the equation of the tangent line, so y minus the y coordinate goes here, okay, equals your slope 1/4 times the quantity x and then minus your x coordinate. Here is the equation of that green line, okay? So the green line, here is the equation. The point it passes through is 2, 5. And the slope is positive 1/4. You can see positive 1/4 of the slope, not too steep. You can tell, and it is a positive direction, so that's what your slope is. Okay? So here we go. Write an equation of a tangent line to a given curve at a given point. All right, so I hope this video helps you get started or work through that. There are shortcuts to getting derivatives, so I'm not sure where you are in the scheme of that concept. However, this is how you would actually use the definition to get the derivatives. So thank you so much for your attention. Appreciate it. Take care. Bye-bye.